Good afternoon, senior 2 students. We're still in chapter 2, lesson 2. The first part, we are gonna talk about the trends and the periodicity of properties in the modern periodic table. In this lesson, we are going to discuss the graduation of the representative elements properties. Representative elements are the elements of S and P block. Of course, we have known that the chemical properties and some of the physical properties of elements depend on their electronic configuration and especially on the valence electron, which are the outermost electrons. In this lesson, we will study the graduation of the following properties for the representative elements. This lesson, we are gonna talk about the atomic radius, ionization potential, electron affinity, and electronegativity. In the following lessons, we are gonna talk about metallic and non-metallic property, acidic and basic property, and finally we are gonna discuss oxidation numbers. Let's start with the first property, which is the atomic radius. We cannot say that the atomic radius is the distance between the nucleus and the outermost electron. And this is because the electron, as we mentioned before in the previous lessons, has wave motion. So it is impossible to know the exact location of this electron around the nucleus. But we use another method to calculate or to find the length of the atomic radius. Number one, the atomic radius, and this term we use it for the covalent compounds. For the covalent compounds, we can measure the atomic radius, which is half the distance between the centers of two similar diatomic molecules. For example, if this a diatomic molecule, oxygen molecule, we have here two nuclei A and B. The distance between A and B is called bond length. How can we get the atomic radius from this? By dividing this bond length, half the distance between A and B is called the atomic radius. So the bond length is the distance between the nuclei of two bonded atoms, but they must be similar atoms in a diatomic molecule. The atomic radius, half the distance between the centers of two similar atoms in a diatomic molecules. So if we have the covalent bond length, we can get the atomic radius. How can we calculate the atomic radius? Before mentioning how to measure the atomic radius, we have to know that the measuring unit of the atomic radius is angstrom, which is equal 1 times 10 to the power negative 10 meters. If the two atoms are identical, so the radius will be equal bond length divided by 2. We have here a solved example to understand this more. The bond length in the chlorine molecule is 1.98 angstrom, and the length between carbon and chlorine atom is 1.76 angstrom. Calculate the atomic radius of carbon. This example will be answered in two steps. Step 1. Calculate the atomic radius of chlorine by dividing the bond length in chlorine molecule by 2. So the atomic radius of chlorine will be 0.99 angstrom. So we have here the atomic radius of chlorine. How can we get the atomic radius of carbon? Simply, we have the bond length between chlorine and carbon, which is equal 1.76, and we have the atomic radius of chlorine. By subtracting both of them, we will get the atomic radius of carbon atom. The second type here, something called ionic radius. For ionic compounds, we use the term ionic radius. Something as sodium chloride, which is an ionic compound, it is found in crystalline shape and it consists of positive cation which is attracted or linked with negative anion by ionic bond. In this case, we have ionic bond length, which is the distance between the centers of two nuclei of the bonded atom. But here you can observe that the two atoms are not similar to each other. How can we calculate the ionic bond length? The ionic radius of lithium is 0.68 angstrom. The ionic radius of sodium is 0.98 angstrom. The bond length of sodium chloride is 2.76 angstrom. We want to know the ionic bond length in lithium chloride formula unit. The first step, we can calculate the ionic radius of chlorine by subtracting the bond length of sodium chloride minus the ionic radius of sodium to get chlorine ionic radius. The second step, we have the ionic radius of lithium plus the ionic radius of chlorine, so simply you can get the ionic bond length of lithium chloride. Before knowing the trend of the atomic radius in the periodic table, let's discuss the effective nuclear charge. Of course, we have known that the nucleus has a positive charge and it strongly attracts the outermost electrons or the valence electron. But in fact, the valence electrons are not affected by the complete nuclear charge of the proton. They are not affected by the complete power of the protons. There is something that reduces the effect of attraction of the nucleus to the valence electron. So the outermost electrons or the valence electrons are affected only with something called effective nuclear charge, which is always less than the nuclear charge, always less than the real nuclear charge. But the question here, why the effective nuclear charge is less than the real power of the nucleus? This is simply due to the screening effect of the electrons of the inner energy levels. Between the nucleus and the outermost electrons, we have here complete energy levels which are filled with electrons. This complete energy levels has a screening effect. They reduce the power of the nucleus to attract the outermost electrons. So the actual nuclear charge that affects the electron in the atom is called effective nuclear charge. After finishing the concept of effective nuclear charge, in the light of this explanation, we have to know the trend of the atomic radius in the same period and in the same group. In group, as you go down the column, the atomic radius increase. As you can observe here, as we go from up to down, you can observe that the atomic size or the atomic radius increased. And this is due to three reasons. Number one, increasing the number of energy levels. Number two, increasing the number of electrons that leads to the repulsion force between the electrons with each other. Number three, by adding new energy level, the screening effect of the inner energy levels to the effect of the nuclear charge will increase. So the effective nuclear charge will decrease and the atomic size will increase. In periods, as you go across the period from the left to the right, the atomic radius decrease. We can observe here that as we move from the left to the right, the atomic radius decrease. And this is because by increasing the atomic number in the same period, number of positive charges inside the nucleus increase. So the effective nuclear charge or the attraction of the nucleus to the outermost electrons increase. So the atomic size will decrease. Don't forget that as we go from the left to the right, the atomic radius decrease, but in the same group as we go from up to down, the atomic radius will increase. Of course, you can observe that the atoms of the first group elements, which are alkalis or alkali metals, are the biggest atoms, while the atoms of group 7a, which are called halogens, are the smallest atom. The biggest atom in the modern periodic table is cesium, while the smallest one is fluorine. Here we have in group 1a, the largest atomic size or the largest atomic radius is cesium, while in group 7a, the smallest atomic size is fluorine. After finishing the trend of the atomic radius in the same period and in the same group, let's know the relation between the atomic radii of atom and their ion. Let's start in positive ions. As you can observe here that the radius of the atom is larger than the radius in the positive ion. So in case of metals that will lose electron and they change into positive ion, the ionic radius will be smaller than the atomic radius. And this is due to the increasing of positive charge. This atom will lose an electron, so the number of positive protons will be higher than the number of negative electrons. By increasing the number of positive charge, the effective nuclear charge of the nucleus will increase, and its attraction force to the valence electrons will increase, and this will lead to decreasing the cationic radius. The opposite for nonmetals. Nonmetals tends to gain electrons and change into negative ion or anion. As you can observe here that the atomic radius is smaller than the ionic radius, and this is because by increasing the number of negative charges, the repulsion force between electrons increase, and this will increase the anionic radius. Let's move to the second property, which is ionization potential or ionization energy. We have mentioned in the earlier lessons that if an energy is supplied to an atom, electrons may be excited and transferred to higher energy levels. But if a sufficient energy is supplied, the most loosely bounded electron may be completely removed, giving a positive ion. This minimum amount of energy is called ionization potential. So we can define the ionization energy as amount of energy required to remove the most loosely bounded electron completely from an isolated gaseous atom. For example, if we have here an atom M, by gaining an amount of energy called ionization energy, it will lose an electron and changes into positive ion. For example, if we have sodium, but it must be in gaseous state, and we give it an amount of energy, it will change into positive ion and the electron will be removed from the atom. You can observe here that the value of delta H will be positive as this atom gain the energy to change into positive ion. Another information here, it is possible to remove 1 or 2 or 3 or more electrons from the atom. So we have first ionization energy, second ionization energy, and third ionization energy. So we have here 3 definitions. The first one, first ionization energy. And this is the energy required to remove 1 electron from a neutral atom and convert it into an ion with 1 positive charge, as shown in the following equation. The second ionization energy is the energy required to convert the positive ion with 1 charge into a positive ion with 2 positive charges. The third ionization energy required to convert an ion with 2 positive charges into an ion with 3 positive charges. And you have to know that the third ionization potential is more than the second ionization potential, and the second ionization potential is more than the first ionization potential. Example: if we have a magnesium in gaseous state and the electronic configuration as shown under the symbol, if this amount of energy is gained by the magnesium gaseous atom, it will lose an electron and changes into magnesium ion carry 1 positive charge. And if we take this magnesium positive ion that carry 1 positive charge and give it this amount of energy, it will change into magnesium positive ion with 2 charges and it will lose another electron. And if we take magnesium with 2 positive charges and we want to convert it into magnesium ion with 3 positive charges, it will gain this amount of energy. Graduation of ionization potential in the periodic table. In the same group, the ionization energy decreases as we go down the group by increasing the atomic number. And you can observe that the ionization potential or the ionization energy is opposite to the atomic radius. As we go down the group, the atomic radius increases. So the complete energy level that screen the attraction force of the nucleus to the valency electron will increase. So we need a small amount of energy to remove the outer electron. As you can observe here from this graph, here is we have group 1A and group 2A. You can observe that as we go down the group, the ionization energy decreases. In the same period, the ionization potential increases as we move from the left to the right by increasing the atomic number. As I mentioned in the previous slide, that the ionization potential is opposite to the atomic radius. As we move from the left to the right, the atomic radius decreases, so the attraction force between the nucleus and the outermost electron increase, so we need more amount of energy to remove the outer electron. You can observe here that as we move from the left to the right, in period 3, the ionization energy increases. Don't forget that as we move from the left to the right, by increasing the atomic number, the ionization energy will increase. And as we go in the same group from up to down, by increasing the atomic number, the ionization energy will decrease. And don't forget that the atomic radius and the ionization energy are opposite to each other. Thanks for listening, Senior 2.